Hello and welcome to PMCD MATHS Teaching Upper and Boundaries of Rounded Values, and this will include working with rounded values to solve problems. As usual, I have the rationale for how I've approached this, and you can pause this to read this. It's all there. Okay, so what I think is not great practice is when you actually have a rounded value, you're asked to find the upper and lower boundary. It might be 6 centimeters, the nearest centimeter, and students just get in the habit of going 0.5 up and 0.5 down from that value to get the upper and lower boundary, and they totally forget what it actually represents. So that they don't really have a good understanding, not showing that understanding of what it's actually representing. So when they get problems like this one here, like I said, 120 centimeters, two significant figures, a lot of time you're going to get students putting 120.5, 119.5. They stop thinking, let's go into robotic. And we have to stay sharp with maths, don't we? All the time, we have to stay sharp as to what's going on. And we only get that if we really fully understand what's going on here. The second part here about the problem solving, about the sharing, you'll come on to a little bit later on when we start looking at sharing a pizza out to look at the behavior of fractions so that we understand, which I think is the most difficult part of upper and lower boundary problems, is when we have a division calculation involved somewhere along the line. Okay, so a sequence of teaching. So you can see I've split it up. Boundary problems involving addition and multiplication, boundary problems involving subtraction and division. You may end up doing that in the same lesson. You may not. It depends on the ability and how they're progressing in that class. You will get that from your regular assessment. So when I introduce bounds, even at the start, sort of come up with a problem, and this happens quite often. I'll give a problem, perhaps we'll return to later on in that lesson or maybe another lesson. Okay, so this is the problem here. I try to use something as realistic as possible, even though they won't necessarily be doing this themselves, but at least they get an idea of how this can cause problems. Will this cooker definitely fit the space? Now, we said on the sequence of teaching that if we express ranges of values with an inequality, if they've got any idea about errors here, they can actually work out an upper and lower boundary. But we haven't taught that yet. So the thing is, we're actually trying to come back to this a little bit later on. It looks like it should fit, shouldn't it? Some people might say it's a bit tight. It's the same measurement, so it should fit. But the key is in here, isn't it? The nearest round to nearest centimeter and nearest millimeter. So that's going to have an implication for range of values that each of those, the space can take and the cooker can take. And just, one little thing I'll say, GCSE papers of old with upper and lower boundary questions haven't been very helpful because they've sort of encouraged this robotic memorization of half units up and half unit down. Things are changing slightly with those more basic questions that are asking for an error bound. So that's a little bit more encouraging to see. So it sort of fits into that, doesn't it? I'll give ideas where things have been rounded. So my height, 183 centimeters, which would have been on an ID card for me at one point. So am I actually 183 centimeters tall? Am I spot on? Am I bang on 100? Why am I 183? What's happened? So with a bit of discussion, you can get to the answer to that. Yes, you're pretty rounded to the nearest centimeter. That means I could be slightly above or slightly below. And so this is where we get into discussion of what heights I possibly could be. So 183, I wasn't so large that I was rounded to 184, and I wasn't so small I was rounded to 182. So when did I start becoming 183? Now, this is years of crafting these sort of questions. What height would I have to be that they would then round it to 183? Okay, so we might get 182.7. Okay, anything smaller, 182.6. With a bit of discussion, obviously you get to 182.5. Okay, and you say, well, that's my lower limit of my height, or we're going to call it the lower boundary. Okay, the lower boundary or lower bound for short there. Okay, so when do I stop being 183? So that's when I start. When do I stop being 183? And again, start to realise that 183.5, I'm going to get that straight away. You might have to ask for a few. 183, quite common, 183.4, 183.41, 183.45, 183.49. 183.49 recurring. Okay, we get that. So, well, that is the maximum possible height I could be. But when do I stop being 183? At the upper bound, which is 183.5, because that actually rounds to 184. And then this is where you link to what they've done with ranges of inequalities, expressing range of values in inequality. We can put a circle above there. We can say my height can be 182.5, because that would round to 183. We can't be 183.5. What is that as a range? Well, I'll put the H in the middle here. It's got to be greater than or equal to 182.5 and less than 183.5, because I can't actually be 183.5. Okay, so that gives the idea. How many heights could I be? Well, I could be an infinite number of heights, couldn't I? Say, well, because is it possible to measure my height accurately? Well, am I ever going to be an exact value? If we had an accurate enough measuring device, mine could be 183 point. My height could possibly be 183.24169, and it could go on. It could be irrational, couldn't it? We don't know. But fortunately, we don't need to know for nearly everything we can be using that for. We don't really need to know what that's going to be, because nearly every number that we use as a measurement is rounded. Football attendance, nice one to use here. It's a discrete value, so you will actually get a whole number upper and lower boundary there. So 51,500 to 52,499. There's no 0.5 there. So nice one to bring out that discrete one as well. 2 litres. Does it make sense? What would that be rounded to? They might say, oh, look, it's 1 litre, 0 litres. Sorry, 1 litre, 2 litres, and 3 litres. You might think, oh yeah, 1.5 to 2. Does that make sense? You have that much of an error on that? So what is that rounded to realistically? Okay, and you will come up probably to the nearest milliliter that we're talking about then. So they have unit conversions there. So there's a lot of discussion in this, and you can start getting to write these expressions out here. So this is where I go with this to start off with, is trying to get them to write a number line for a rounded value with the appropriate notation to show what's included and the inequality. Okay, so then I give a bit of practice with those, and upper limit, lower limit, and inequality. So there's a few of those, and that's this is how I get them to lay it out. And I'm asking for them to use the diagram as well. Okay, so I expect them to have a diagram there. So here, show the range of possible values, a number line labeled with lower and upper limits or bounds. I suppose boundaries is probably what I'd go with. Now, just going back to that, there is a lot of argument about 183.49. You can't be 183.5. No, I mean, I talk about this when I say this sort of language I give as well. This is a boundary. Yeah, imagine your garden. Within your boundary, within 2 fences, okay, of a garden, you own all of that, don't you? That's all yours. It belongs to you. Within that boundary, all the values belong to 183, or all those values will round to 183 within that. On the boundary itself, well, one of the boundaries is included, and one of them isn't. And I think this just simplifies things rather than having to use 183.49 recurring. And we can get into the argument is what's the difference between 183.49 recurring and 183.5, which is a whole other interesting thing to look at. But bounds is where I'm going to go with this. Okay, so upper bound and lower bounds. And what do we go on to next? Right, so then after we've done sort of lesson on that and they got happy with that, upper and lower boundary problems. Stephen's 120, should he be allowed to ride? Okay, now if we're to the nearest centimetre, if he's actually 120 centimetres, he could be half centimetre too tall, couldn't he? And if that ride, its safety limit is at 120, he could be getting a headache. Now probably I'd imagine that there's much more limits built into these measurements than there's actually there. There might be actually another 5 or 10 centimeters that it could be, but it's good discussion, isn't it? So they see these things in everyday life. They think about the implications of where's this come from. Okay, so it's a nice little starter, I think. And we're looking for multiplication and addition. So I'll use in perimeter and area of a garden here. I start off with something open-ended now. I don't give them any structure to start with. Can they tell me what length of fencing should be so she can surround the garden? And then I go on to what area of garden is now, what's the maximum area of garden that can be fenced with this, and the minimum area of garden that she can fence. But she has to be sure that she can surround the garden. And that's to the nearest metre now. Afterwards, you can question, is that realistic? Would you round to the nearest metre if you're doing measurements or not? Probably to the nearest centimetre. Is that going to make a huge difference? Maybe even the nearest millimetre. Is it going to make a huge difference if your boundaries are out? So why don't we see gardens with great big holes around the side? Because people haven't taken account of boundaries. Probably because they're rounding to a more accurate measurement than nearest metre. But it's nice to throw these things in there because they accept this to start off with. And, oh yeah, it's the nearest metre. They'll accept that because they haven't got the practical experience to understand what you would actually do. So if they do need help, then I put in a bit of structure there. Okay, upper and lower boundaries, maximum perimeter, minimum area of the garden as well. So that's addition multiplication. That seems to make sense, doesn't it? Because when you're adding two values who have been rounded, the upper boundary is going to be the upper bounds added, and the lower boundary is going to be the lower bounds added. I should change that to bounds really here, shouldn't I? Rather than having limits, but you get what I'm saying there. But the real challenge with this, I think, because this, if you throw this at them straight away, sorry, there's an abstract version of this as well. Okay, so you can cover up and show, cover up on the ability of the class. You don't have to show this. You can the y upper and y lower. You can actually leave that and let them work out what to do with that. But the challenge, I think, is division. So I start off with a little activity like this, just to get the idea, as I said, about understanding how fraction value changes. And it is obvious, but it's worth going over in the context of the problems we're going here. So he ordered 6 pizzas for his maths class of 18 pupils. Obviously, the fraction he's going to get is 18 pizzas. 6 divided by, 18, which is a third. But we're going to leave 6 over 18 for now. Okay, so what have we got? Number of pizzas divided by the number of pupils. And I ask, well, how can we increase that size then? Let's just put equals a third. How can I actually increase the slice size for people? What ways are there of doing that? Well, it's 2 ways. We can increase the number of pizzas, or we can decrease the number of pupils. Okay, so if I want maximum size pizza slice, fraction is going to be pizza slice, the numerator is going to be the largest it can possibly be, and the denominator is going to be the smallest it possibly can be. Okay, and that is going to give you your largest value. Okay, that's going to give you the maximum value you can get. The minimum, obviously, if we have the smallest, so the minimum would be equal to the smallest number of pizzas and the most number of people. You can imagine that party is not going to be much fun, is it? Okay, so this leads on to then understanding how we're working with fractional problems with upper and lower boundaries. Because if we have a fraction where we're trying to find the maximum value or the upper boundary, we need the largest numerator and the smallest denominator. And then we can go into a problem here. So the problem I get, now, I don't even know if this thing actually exists or it's a toy, but anyway, I thought it was an interesting thing to sort of discuss here. This Coke container. So they're going to do the upper and lower boundaries. That's the nearest litre, the nearest milliliter. Okay, so we have got an issue in that there's unit changes here. They're going to have to be aware of that. And what's the maximum number of cans that can be filled by the tanker? What's the minimum number of cans can be filled by the tanker? Obviously, it's going to be, we've got a division here, haven't we? So the maximum would be the volume of the tanker upper divided by the can of the Coke lower boundary. this gives it something, you know, hopefully a little bit of interest into what they're doing here, rather than just giving something dry and abstract at this stage. We are going to deal with abstract in a second, but this is to start off with. So how many cans of Coke can we actually fill from this tanker, if it exists? I mean, I pretend it does exist. I'd like to think it does exist, but I've never seen one on the road. Okay, so that gets into that. So we hope you've got the background for that. And moving on, I've got an extension task here. So there is an extension task on this if they get through that very quickly, but I think it's worth discussing both of these actually. 12 plus h over y, 12 subtract h. So that comes in, brings in this subtraction here. Now this is really interesting, good one to just discussion here. This was not so bad. You want that to be, you can get the upper and lower bound, upper bound for s and the lower bound for s by doing what we've done, because it's addition. It's going to be, the upper bound is going to be upper bound of h divided by the lower bound of y plus 12. But here, on the upper bound of s in this case, okay, you've got to think about what's happening with subtraction here. And you know, if you've seen this before, it's very easy to miss these out. But if you've seen this before, what you want for the upper bound is you want that fraction to be as small as possible. You're subtracting, which means you want h lower over y upper. So it just it makes them think a little bit more here. Okay, so what do I follow up with? Well, the classroom activity for this, I spent a long time putting this together, and this is all on worksheets on this flip chart. So if you have got Promethean, I can attach this and you can use this if you want. What I did is I printed out, now you're going to see on the left hand side here, you can see there's green, amber, and a sort of red there. Okay, now green, amber, and red, so is indicative of difficulty of the question. So red, amber, green being the more challenging ones here. So what I did is I sent this off to Reprographics. I made up the cards. I stuck them on, and I asked, once I'd done that, on the back of the card, I put my solutions. Okay, and even put marks. I would give this. These are all past GCSE questions. Each card, that's 1, that's 2 with its answer, that's 3 with its answer, and so on. And I've got, how many have I got altogether here? 9. Okay, so I did probably 3 or 3 copies of each. I can't remember how many I did now. The idea is that students are working in pairs anyway. Okay, so they have to come up with this. You have to get trust involved here, but once they've done the question, they can turn over, they can answer it and mark it according to the mark scheme that I've given. And once they finish that, they swap it with somebody else. So there's 9 different questions there. Some are easier than others. For example, this is one of my favourites. You may have seen this past GCSE exam. Really interesting, and it generates a lot of conversation. So be careful if you do give these out. I wouldn't give this to a student that's just managing to grasp it. It'll blow their minds to start off with. There's 9 of these, as I said. Okay, now I'll tell you what I can do. I mean, let me just go through this. 1, if I do it like this, 2, what you could do is you can freeze and you can screenshot if you want to use this. Move this out of the way. Move this to the side. This is a lot of work, as you can see, but this is what I was saying about the whole process. The whole reason I'm doing these videos, I'm trying to encourage people to be creative. I think sharing is a good idea, but we've all got to be able to contribute to that sharing. And you know, if you don't create something yourself, you don't have any of your personality in it, and it's not yours. You know, when I'm teaching this, I've designed the way this runs, so I'm very involved and very attached to this, and it comes through in the way that I teach it, I think. Okay, and you know, another question there. Okay, so hopefully that's given you some ideas about what you might like to do when you're teaching upper and lower boundaries. Maybe new ideas, maybe adding to ideas that you've already got. Let me know what you think. Let me know if you've got your own ideas. And I thank you for watching, and I'll see you next time.